When you take the negative derivative of potential energy with respect to position, you get the expression for the underlying conservative force. The goal of this video is to see how incredibly powerful this equation is and to develop a brand new intuition behind it. So let's begin. All right, the first question for ourselves is, what exactly is this equation telling us? It's saying that the force equals a negative rate of change of potential energy with respect to position, which means if we can visualize a potential energy graph, then the force has something to do with the slope of that graph. But let's dig deeper. Let's think about the magnitude and the direction of the force. If you only concentrate on the magnitude of the force, the strength of this force, then we can ignore the negative sign. That equals, what is du over dx? Well, that represents the slope, right? But slope of what? It's the slope of the graph of potential energy versus position. We'll just call that as potential energy graph. So our first insight is that the magnitude of the force is given by the magnitude of the slope of the potential energy graph. Okay, now let's talk about the direction. What is this negative sign saying? Well, think about it this way. If du dx is positive, that means the change in potential energy is positive. That means that the potential energy is increasing. What is negative of that? Well, the potential energy is decreasing. So this equation is telling us that the direction of the force is in the direction where the potential energy is decreasing. So our second insight is that the direction of the force, well, it's in the direction where the potential energy is decreasing. So now let's put it in action. In fact, let's consider an arbitrary system. Let's not worry about whether we're dealing with system of springs or gravitational force. Let's not worry about which conservative force we're dealing with, but let's just consider a random system, okay? Let's say that the potential energy graph looks like this, some random graph we have. What is this graph trying to tell us? Well, what this is saying is that in that entire system, whichever system we're dealing with, if we pick one particle, okay, then how does the potential energy of this system change as the position of that one single particle changes? So when the particle is at origin, the potential energy is this much. When the particle comes from here to here, the potential energy reduces. Then the potential energy increases, then the potential energy reduces, then the potential energy increases. So you can see it's a very, very complicated system. So let's not worry about which system we're dealing with. But the question now is, can we gain some insights about the force that is acting on that particle? So let's think about its magnitude and direction separately. So what we see is that the magnitude equals the slope of the PE graph. So let's analyze the slope. As I start from here and I go towards the right, notice from here to here, the potential energy is reducing. I don't care about that. What I care about is the slope. The slope is pretty much a constant. So I can say that the force, the underlying force acting on my particle, is pretty much a constant from here to here. As I go from here to here, the force is pretty much a constant. But then what happens to the slope as I go from here to here? The slope, look, it's becoming less and less steep. It's becoming flatter and flatter and flatter. And eventually at this point, the slope is 0. That means at this point, the force, or at least the x component of the force, because you're only considering one dimension, okay? So the force in the x direction, that goes to 0. This means if that particle is over here, remember, this is where the particle is allowed to move. It's one-dimensional case, okay? So if the particle is over here, then the force acting on that is 0. In other words, our particle will be in equilibrium. So now we have some insight about how the magnitude or the strength of that force varies as we go from here to here. It's pretty much a constant and then it reduces to 0. So let me use some dots to represent it. So the size of the dots is, representing the strength of the force. So it's pretty much a constant and then goes to 0. It's not very quantitative, it's very qualitative, okay? All right, now what happens as I go from here to here? It'll be a great idea to pause the video and think if you can comment on the strength of the force for the rest of the graph. All right, so as I go from here to here, the potential energy increases, but I don't care about the value of potential energy. I care about the slope. That's what this, the force depends on. So let's look at the slope. This, it starts from 0 at equilibrium point, and then the slope increases. It's becoming steeper and steeper, steeper, and then the slope decreases and you go back to 0. So you get another equilibrium point over here because the slope is 0. So how does the force varies? Well, it starts from 0, increases, and then decreases back to 0. Okay, and then what happens when I go from here to here? Well, again, look, the slope increases. Ooh, it becomes very steep at this point. So the magnitude of the force will be very strong. And then again, goes to 0. You find another equilibrium point. So we get a very strong force at this point. The force value is very strong at this particular position. And then finally, as I go from here to here, what happens? Well, again, the strength of the force increases drastically, very strong slope over here. So very high force over here. Strength of the force is very high. And then again, eventually decreases to 0. And then look, the slope is pretty much 0 because it's flat. So from here to here, the force increases, decreases, and goes back to 0 and then stays 0. Isn't this wonderful? I mean, think about it. This is some complicated system. I have no idea. And yet, just by looking at the potential energy, I can comment on what's happening to my force. That is the power of potential energy graphs. But this is just the magnitude of the force. We can now also comment on the direction. Okay, let's think about this. Remember, the direction of the force is always in the direction where the potential energy is decreasing. So let's consider this section over here. As I go to the right, the potential energy is decreasing. If I go to the left, the potential energy increases. So which direction should be the force? The direction in which the potential energy is decreasing. So the force in this side, in this particular region, is to the right. Now this is not representing the magnitude. This is only useful for direction. We already have insights about the magnitude, okay? Okay, what is the direction of the force in this region? Well, let's see. If I go to the right, the potential energy increases. If I go to the left, it decreases. It's in the direction where the potential is decreasing. So at every point over here, the force would be to the left. Again, it would be a great idea to, think about the direction of the force in this region, and this region. All right, let's do this. Over here, the right side is where the potential energy is decreasing, so the direction of the force is to the right. Over here, if you go to the right, the potential energy is increasing. If you go to the left, the potential is decreasing, so it's to the left. What is the direction of the force over here? Hey, the force is 0, so it doesn't have a direction. And so what is so incredible about the potential energy graph is that not only do I have insights about the magnitude, but I also know the direction of the force. So if I put it together, I can say as I start from here, the direction of the force acting on this particle in this complicated system is to the right to begin with, okay? And then it pretty much stays a constant, and then it reduces, goes to 0, and then it flips over, and then again the strength increases, goes back to 0, and then again it flips, and then the strength increases drastically, again goes back to 0, and again it flips, increases drastically, goes back to 0, and then it stays 0. From here onwards, the particle does not experience any force. Isn't this incredible? But there is more. Look at these equilibrium points, okay? If I were to keep my particle over here, then the force acting on my particle would be 0. It would stay put. But what would happen if I were to nudge it slightly to the right? Well, then the force is to the left, so it'll move back to the left. And then what if it gets nudged slightly to the left? Then the force is to the right, it moves back to the right. Notice that the system is trying to push this particle back towards the equilibrium position. Such equilibrium positions are called stable equilibrium. And it makes sense, right? If you nudge it a little bit, it'll tend to come back. The system drives it back to that equilibrium point. The same thing applies over here. Notice the force is driving it back, the particle back to the equilibrium position. So this is also a stable equilibrium. But what about this point? Even here, if you were to position the particle at this location, the force acting on that at that particular location is 0. But what happens if you nudge it a little bit? If you nudge it a little bit to the left, look, the force is no longer driving it back to the equilibrium, it's taking it away. If you nudge it to the right, again, look, the force is taking it away from the equilibrium position. The nature is no longer driving it back. Instead, it's driving it away from the equilibrium position. So good luck trying to keep a particle, stay put over here. Small nudges will take it away from the equilibrium position. And therefore, this is called unstable equilibrium. So look, maximas in your potential energy graphs are unstable equilibriums, and minimas, local minimas, are stable equilibriums. Why? Well, because think of it this way. When you're at a minima, on either sides, potential energy increases. And so system tries to drive it back to the decreasing direction, and so it tends to drive it back over here. But when you're at a maxima, on either side, the potential energy decreases. So on either sides, the force is directed away. So notice forces tend to lower the potential energies. It's always directed in the direction of lowering the potential energies. So not only do I have insights about the magnitude and the direction of the forces, I also have insights about which points are stable and which points are unstable equilibrium. All right, but here's a last question for us. What if this entire graph was shifted upwards? The potential energy values everywhere has now increased. But does that change anything as far as our forces are concerned? No, it doesn't, because the slopes stay exactly the same. And all I care about is the slope. I don't care about the actual value of the potential energy. And that is very, very reassuring, because remember, the actual value of the potential energy at any point is quite arbitrary. It depends upon where you choose your zero to be. So as you change your reference for zero potential energy, this graph will shift up or down, but it doesn't affect the underlying force. That's what we would expect. We wouldn't expect the force acting on a particle to change based on what we choose as our zero reference point. So that is also pretty reassuring over here. So if you put it all together, look at what this graph looks like. It's as if that this is an actual hill or some kind of a racetrack, whatever you want to think about it. And then if you were to put a marble over here, it would behave exactly the same as the actual particle. Remember, this is not a real hill, okay? It's a graph, all right? But if you were to put a marble over here, for example, look, it would roll down, and the force at this point would be pretty much a constant because it's a constant slope. And then notice that if you were to put a marble over here, it would pretty much stay put at the equilibrium point. If you nudge the marble, it'll come back over here. This is also an equilibrium point, but good luck trying to keep the marble at that point, because you know intuitively if you nudge it a little bit, it goes away. You cannot, you will not get back. The marble will not spontaneously come back to this point. You have another equilibrium point over here. If the marble was at this location, we know it's so steep, the force acting on the marble will be very high. So what this all means is that when you look at a potential energy graph, you can assume that it's a hill or it's some kind of a racetrack, and you put a marble over there. Whatever happens to that marble, the same thing will be happening to the actual particle. So it makes this analysis that much more intuitive. This is why we love potential energy graphs. Whenever we are dealing with very complicated forces like this, instead of writing an expression for the force or even trying to draw the graph of a force, it's much more useful to draw the potential energy graph, because not only does it tell us about the magnitude and the direction of the underlying force, it also helps us predict intuitively how the particle would move under such complicated forces.